Hi, this is our work on pre-training GNNs with the geometry of molecules to improve their predictions of molecular properties. And if we're talking about doing message passing or using GNNs on molecules, what we mean is the molecular graph where the nodes of the graph are given by the individual atoms and the edges of our graph are given by the atomic bonds between the atoms. And then we just do message passing, use some GNN on this molecular graph and end up with some node embeddings in the end that we then pool in a final step to end up with a fixed size representation that we put through another MLP to predict some properties like the activity or the stability or toxicity of a molecule, which is of course important information. But we also know that while these GNNs or this message passing on just the 2D molecular graph really works quite well already, we also know that we can get much better, much more accurate predictions if we additionally use the 3D structure of the molecule as input. So with 3D structure, I just mean the individual coordinates of the atoms. If we use that as additional information, we can really sometimes get up to 5 times lower mean average error. But obtaining this 3D information is quite expensive, and in situations where we want to make predictions for billions of graphs, it takes too long to generate this 3D structure with computational methods, and we're stuck operating purely on the 2D graph for which we can't make this accurate predictions. Yeah, so what we now want to do is to find a way to implicitly use 3D information when only having 2D information available as input. And the way we want to do that is that we leverage the small subset for which we have the 3D structure. So the small subset of molecules for which we do have the 3D structure, we leverage that in a pre-training task. And in this pre-training task, we have a 2D network and a 3D network, where the 2D network just takes the molecular graph and generates a 2D representation, and on the other side we generate a 3D representation. And then we maximize the mutual information between those, so maximize the similarity. And this way, with contrastive learning for example, and this way we force the 2D network to learn to encode some 3D information in its latent representation here, just with the 2D input. And then we just take all the weights of the 2D network, we transfer them, and then we fine-tune them for the actual property that we're interested in. And this way, and that's what we now do on the molecules for which we don't have the 3D information available. And this way, just with the 2D input, the 2D network has learned to generate some latent 3D information, and that information can then be used to inform our downstream predictions. Yeah, and if we do this pre-training task, we can see that here we have the numbers that we get if we don't do the pre-training, and the arrows here indicate whether higher or lower is better. And here we don't do our pre-training, here we do our pre-training. So when we're using the QM9 dataset and predicting the HOMO property, for example, so some energy, we can really get a much lower mean average error. So this pre-training really works, and I hope you enjoyed my presentation.